ご飯ご飯食べますか？
食べます。
食べます。How do you feel after? How do you feel after poster?
Interested.
Many difficult questions. So. Okay. お疲れ。
But I study professor comment.
すごい。
すごい。
Who's the professor?
And professor and company.
Company.
Yeah.
Not only university, but from the company. Okay. お疲れ様です。
お疲れ様です。
What do you think? What do you feel after poster session?
Freedom!
お疲れ様です。
ありがとうございます。
夏美さん、
Yes,
What are you feeling now?
very nervous.
Very nervous.
Yeah.
I hope you can go through with spirit, with the best. 頑張ってください。
ありがとうございます。
You're welcome.
さんも頑張ってください。
ありがとうございます。Good morning, Professor and fellow scholars. Today I would like to present my recent study about synthesis of vertically lined carbon nanotube PDMS composite to control surface lateral stiffness and its measurement. We start about research background. The cell differentiation is one of main part in regenerative medicine. The issue is to enhance the number of differentiated cells. So MS is after stimulated by chemical cues and material and mechanical cues with specific stiffness is soft or hard, it will transfer or differentiate and become osteoblast, adipocyte, or myocyte. And cell respond to mechanical cues. Fu et al. Find that cells are more active in lateral direction, as shown on the figure. But the issue is the diameter of pillar have not given direct high tension on cytoskeleton to nucleus. Wong et al. On the other hand, find that the lower cell membrane angle increase cytoskeleton tension and enhance MSS differentiation. But the issue is the microwell he made, which is flat surface, on nucleus to tend to be flat shape. So we choose vertically lined carbon nanotube as a substrate because of two reasons. First, VSCNT have diameter in nanometer that is expected to increase the cytoskeleton tension. Second, VSCNTs maintain the nucleus cap in 3D shape. Here I show you the research purpose is to control lateral stiffness of VSCNTs in composite by using different H of PDMS. PDMS took part as a restraint of VSCNTs from bending. We have three samples. First, composite with higher PDMS, and second with lower PDMS, and VSCNT only without any PDMS. The hypothesis is the higher PDMS thickness will make an increase of lateral stiffness of VSCNT surface. Here, the procedure, we present a novel method where the fabrication occurred on PDMS liquid and rapid curing, so which keep the PDMS elasticity. These are the 3D stages. First, synthesize the two components separately to transfer and rapid curing on 100 Celsius degree hot plate in 3 minutes and substrate removal. Here is the PS synthesis with two stages by using ECR avionics, catalyzed deposition of FA catalyst, and then bring the substrate to the TCFED to grow the CNTs in 700 Celsius degree in 7 or 8 minutes with 22 micron of H. And we choose the PDMS H, according to the spin coating speed, 8.6 and 6 micrometer for first and second composite respectively. And here I present the PACNT's PDMS composite result, that we can see that the first composite has higher escalation than original PDMS at 16 to 20, and has 0.5 to micron of CNT bundle distance, and it's quite wider gap. And for the second, on the other hand, has H distribution good with 7.5 H of PDMS with quite small distance of bundle distance, and this one is PSCNT with nanometer distance. And we continue to measure the lateral stiffness, that was acquired from LFM method by using SPM 9700. So LFM is moving the cantilever horizontally that produce lateral value from the twist of the deflection of the cantilever. We choose 10 micron because we make sure that the diameter is suitable, that the probe didn't slip deeply into the CNT forest that will make noise and unreadable data on the LFM results. We set an axial force is as an input with specific velocity. After that, we can measure the lateral stiffness from stick slip phenomenon. That the peak of stick is the widest gap between the equilibrium, and the lateral force are obtained from the convert of deflection twist of cantilever, and we got the unit volts per meter or nano per meter. Here I present the LFM measurement. The first composite has higher FL value compared to the second, and the PSCNTs as an increase of axial force value, all the data show a decrease of lateral force. And this one is the conversion, 0.001 means or equal 0.04 nanonewton, and etc. And how to get the lateral stiffness? So first we read the probe here slipped slightly into the between of CNT bundles, 2 and 3 stages. The probe collide the CNT bundle for going up, and the fourth step, the probe are then slide stably on the CNT tip end. And here we measure the lateral stiffness, and this the graphic looks like. The lateral stiffness here is the result, and here is still kilovolts per meter because we need a method to convert lateral force value to Newton. First composite show the result 100, and the second lower, 1800, but the VSCNT that's so high, but it's not represent the CNT bundle individual value because of the high density of the distance between the bundles, so that make the lattice spacing is steep and short. So the conclusion is we have fabricated functionalized PSCNTs with PDMS in a novel partially compositing process where PSCNTs tip end are free to move. And second, by controlling the PDMS thickness, we can control the lateral stiffness of PSCNT surface. And we can suggest that PSCNT's PDMS composite is compatible and could be used for cell differentiation based on its controllable and measurable lateral stiffness. Thank you very much.
Thank you for your interesting talk. 会長の皆さんから、コメント質問がありましたらお願いします。 私から意見、have you ever tried to sell culture on your substrate?
Yeah, I have cultured it.
How was the result? Sales, as you predicted, sales were spread on the substrate.
Yeah, so let me show you. So why I said it increased the cytoskeleton tension, because the morphology, after I tried with preliminary experiment, it showed small angle of cytoskeleton tension near the nucleus, and I missed the image here.
I'm sorry, I can't catch your concept of your studies because do you think about how to measure the cellular traction force by using your PR-like vertical line circuit? How did you measure the cellular traction force?
I didn't measure cell traction. I measured the property of the carbon nanotubes either. So yeah, I measure the individual bundle of the CNT.
Are you planning to measure the cellular traction force by using your this PRs?
Cell traction force.
Application for your application.
So this only works on the CNT bundle, but to measure the cell traction, we need to label. We need to label the tip of CNT after we bundle, so we know the movement of the
It's too difficult to measure the diffraction of the field.
Yeah.
Thank you.
Thank you.
For the last result, this one, how come VACNT comes really high value compared to the other two detectors? It is supposed that I couldn't get the point of the last explanation. Could you
Okay.
just explain?
Okay, sir. So first, this one is stiffness. If we convert it, it will be Newton per meter. But this VACNT is so high because the lateral stiffness is based on lattice spacing. So the VACNT is here. The gap is really small in nanometer. So it makes steep, really steep, that make higher number of stiffness. So actually, the measurement for CNT, this one is not the result is not reliable. So we need to make the CNT become like this, have the gap like this, have the gap like this. So the result will be reliable.
Okay, I just realized that CNT bundle with is different. I just realized it.
Thank you.
おおむね時間になりましたので、この発表終わりたいと思います。Thank you for your presentation.
What do you feel after presentation?
I'm happy.
I'm happy.
So happy.
Glad you do great job.
Thank you.
お疲れ様でした。
お疲れ。リコさんもお疲れ様でした。
いえいえ。
いえいえ。
永遠に貼っと
入ってないです。さよなら。さよなら。小山一層
Toyama is so great. The sake is really nice, but I don't drink. Just